Today we are talking about compound inequalities. And you might remember or have heard of a compound word before. A compound word, remember, is a word like two words put together. That race car is an example of one, and toolbox is a one. You got two different words that come together, and they form one word with kind of an extra meaning then. A compound inequality is kind of like this. At first glance, you might think it's two different inequality statements, but because of how they're connected, they actually form one thing. So, there are sometimes, some situations, there might be several different requirements that have to be met in order for something to be a solution. You've certainly been given assignments where you have several different requirements that you have to meet in order to get credit. That can happen with numbers as well. Several different things have to be true before something counts, before it works. And with math, we tend to separate statements like that with the word and. If you see the word and in math class, that has a really specific meaning. It means that both of these statements must be true in order to be a solution. So, as an example, we've got two different statements. X is greater than or equal to 5, and x is less than 10. And you might think that those are two separate little things, but that is one inequality. And this whole statement has to be true in order for numbers to be solutions. So, here's a couple of numbers to test. What about 3? So, is 3 greater than 5? No, it didn't meet that first requirement, and so 3 is not a solution. Is 5 greater than or equal to 5? Yes. Is 5 also less than or equal to 10? Yes. So 5 is a solution. Has to make both things true. Is 8 a solution? Sure. 8 is greater than 5. 8's less than 10. 8 works. What about 10? 10 works. 12. Does 12 work? No. And there's lots of other numbers I could have thrown into the list, but I just picked out a handful. And remember, a graph is all of the numbers that work. We shade the numbers that work, and we don't shade the numbers that don't work. And so numbers like 5 and 6 and 7 and 8, 8.5, 9, 9.9, 10, all those numbers work. So I'm shading them. And we tend to emphasize the boundary points, putting little circles there. Are these circles supposed to be filled in? Yes. In this case, yes, because 5 works and 10 doesn't. So, one additional thing about AND graphs is AND graphs can be rewritten in a little different way. You can write an AND situation as what we call a compound inequality by kind of squishing things together. If I take x is greater than or equal to 5 and I reflect it, that gives us 5 is less than or equal to x. And I also have x is less than or equal to 10. If we kind of share x's there, 5 is less than or equal to x, and x is less than or equal to 10, I can write that statement like this. I like to call that sort of thing a sandwich inequality. I think I'm the only one that calls it that, but maybe other people do. I don't know. But if you ever hear me say a sandwich inequality, that's what that means. Now, when you have a compound inequality or a sandwich inequality like that, it kind of, I like working with these things. I feel like I'm being really efficient when I'm working with these things because you can solve a compound inequality like that by doing moves on it. And you treat this three-sided thing just like you would a two-sided thing, but with 3 sides. If you wanted to do moves on this to try to get x alone, like dividing by 2 or subtracting 10 or that, you can do that, and you do it to all 3 chunks. I like to say that you might add 10 to the left side, to the inside, and to the right side. So what should we do to try to get x alone in the middle there? I got 2x plus 10. I want to try to whittle this down to have just x. Subtracting 10 is a good move. I'm going to do that to the inside, and to the left side, and to the right side. So, when you do that, you have 2. The insides becomes just 2x's. The right side becomes 20. And we still have to think about flipping the symbol or not. When I add or subtract, do I flip or do I leave it? Leave it. So still less thans. Now I've got 2 x's in the middle, but I just want x. So to get rid of the times 2, divide by 2. And so 2 divided by 2 is 1. 2x divided by 2 is x. 20 divided by 2 is 10. And do I have to flip the symbols or leave them?
Leave them.
Again, we'll leave them as less thans. And the last statement I have here, that 1 is less than x is less than 10, that's equivalent to the original. They both have the same graphs. The same numbers make those things true. But the bottom one's a lot easier to graph. 1 is less than x is less than 10 suggests that the numbers between 1 and 10 are what makes the statement true. And so a graph for this is pretty simple. If I get out a number line, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so forth, negative 1, negative 2. In between 1 and 10, I need to shade. What about 1 itself?
No.
Yep, that one's left open, and 10 is left as an open circle as well. I should tell you that the endpoints aren't always the same. Sometimes 1 is filled in and 1 is not. You could make that happen if you had a or equal to on one side but not the other. Then that boundary might be filled in and the other one not. So make sure that you actually look at each boundary and is there a less than or equal to or not. So that's and graphs and compound inequalities. It's also possible that instead of having several requirements to become a solution, you can also have several options that might allow you to become a solution. This would be a little bit more flexible. There's more ways to become a solution. There's more ways to get credit. There's more ways to do what you need to do. So this is a little more flexible. When that's the situation, we separate inequalities with the word or. So in the example that's here, x is less than 0 or x is greater than 7 means there's 2 options, 2 ways for a number to become a solution. That should result in more solutions then, because you've got, if you don't make it the first time, you've got a second way to possibly get in. So here's some specific numbers to throw in there. Is negative 2 a solution? Well, is negative 2 less than 0? Yeah. So it's a solution. It made it. Yes, negative 2 does not make greater than 7 true, but that doesn't matter. It doesn't have to. It just needs to get in somehow. So negative 2 is a solution. What about 0? Is 0 less than 0? No. But there's a second chance. Maybe 0 is greater than 7. Is 0 greater than 7? No. Oh, sorry, 0. I gave you 2 chances. You didn't work, so you're not a solution. Try 3. Is 3 less than 0? No. Nope. Well, try is 3 greater than 7? No. No. All right. Sorry, didn't work. What about 5? Nope. This reminds me of a song. I gave you 2 chances, and anybody know that song?
No.
Little Bunny Foo Foo, right? So, anyway, moving on. If I put 8 in here, 8 greater than 7? Yeah, 8 works because it makes the second one true. So 8 is a solution. 7.5 would also work. I didn't put that one in here. If I wanted to make a graph of this, the most important numbers on my graph are 0 and 7, the boundaries. And I want you to realize there's kind of 3 regions in this number line. There's the numbers before 0, which worked because they made this one true. There's the numbers in between, which didn't work. And then there were the numbers beyond 7, like 8, 9, 10, even 7.5, that work because they make the second statement true. So the graph for this is all these numbers and all these numbers, but not the ones in the middle. What about 0 and 7? Should they be filled in? No. Or in this case, they should be left open because there was not the or equal to. So this is our complete graph. And I'll tell you, or graphs usually look like this. Or graphs are almost always two numbers as boundaries and the outsides shaded. One word of warning, or graphs cannot be written as sandwich inequalities. You might think that you could because, well, let's try. 0 is less than x, and, no, what was it? It was x has to be less than 0, and x has to be greater than 7. And if I reflected this, I could get 0 is greater than x, and then x is greater than 7. It seems to look like it might work. But if you look at this statement as a whole, this statement as a whole is inconsistent. 0 is greater than x is greater than 7. 0 is greater than 7? No. And there's no numbers that will work that will kind of fit here because there's no numbers that are greater than 0 and greater than 7. So in general, you may not write or graphs as compound inequalities. So in summary, and graphs, if you have two inequalities separated with the word and, that means that every one of the statements involved there, both of them usually, will have to be true in order to be a solution. I'd suggest that you jot this little picture down in your notes too. And graphs is always the shading in between. Or graphs, on the other hand, mean that either one of the statements will work to become a solution. And or graphs produce pictures where the outsides are shaded. They're kind of opposites in a way. And is the stuff in between boundaries, and or tends to be the stuff outside of the boundaries. Thought we should do a few other examples. This is very similar to what your homework's going to look like today. So here's what we call a compound inequality. 5 is less than 2x plus 3 is less than or equal to 15. I'd like to eventually make a graph of this, but before I do that, let's try to solve it. Let's try to get x alone in the middle. And so what moves should we do to get x alone? Subtract 3. Do it from all three sides. From the left side, from the inside, and from the right side. 5 minus 3 is 2. 2x plus 3 minus 3 is just 2x. 15 minus 3 is 12. And the symbol will stay as less than or equal to's. Then I'll divide to undo the times 2. I'll divide by 2, and I'll do that on the inside, the left side, the right side. I have 1 less than or equal to x, which is less than or equal to 6. And compound inequalities, the graphs for these, 1 and 6 are your boundaries, and you shade the stuff in between. So if you wanted to make a graph of this, 1 and 6 are the most important numbers on the number line that you'd have to find. Shade in between them. And last part of this is 1 and 6, are they supposed to be shaded or left open or not? In this case, 1 is supposed to be shaded because it has the or equal to clause, and 6 is also supposed to be shaded because it has that or equal to clause. So they both are shaded. There's our complete picture. All the numbers between 1 and 6 inclusive, sometimes we say. That's our answer. Another example. I bet some of you will see this particular problem on your worksheet tonight, and you'll think, oh, good, I can do whichever one of these I want to do. And it looks like the 4x16 one. That looks simpler, so I'll do that one. That's not how it works. OR graphs don't mean that you get to choose which one of those you do. OR graph means there's two different ways that numbers might become solutions on the same number line. You got to think about both of these. You got to simplify both of these and eventually come up with a graph. And there's probably two different regions on that graph, unless they messed up or they overlap or some weirdness happened. So let's go a second and solve the first one. To get x alone there, I would recommend subtracting 5 from both sides, which gives us 3x is less than or equal to 6. Didn't need to flip because you don't flip when you subtract. Divide by 3, and x is something 2. Do I flip here because I divided? No, because it was positive 3, so it's still less than. So that's one way that a number might be a solution. Numbers like 0 and 1 and all the negative numbers would have to be shaded. But there's another way that numbers could become solutions as well. And we need to solve the negative 4x is less than 16, example 2. How do I solve that? Dividing by negative 4. Negative 4x divided by negative 4 is x. 16 divided by negative 4 is negative 4. Do I flip the symbol or not? So, yep, I flip the symbol. So, greater than negative 4. So, here are two different ways that numbers can become solutions. I'll break out my number line now. So, 0, 1, 2, 3, negative 4, negative 5, negative 6, negative 7, so forth. And 1, 2, 3, 4, 5. This is certainly big enough. And probably the most important numbers on this graph are 2 and negative 4. So I'll go ahead and find those. Here's 2 and negative 4. And I'll put a circle there and a circle here. And I usually, when I see an OR graph, I think the outsides are going to be shaded because that's what OR graphs typically do. This one, I'd actually encourage you to look at it a little more carefully. This one's kind of a trick.
Oh boy.
If we look carefully and remember what shading and graphs mean, numbers that make this true need to be shaded. And I recommend, let's test a number in each of the different chunks of this graph. Let's test a number in this region. Let's test a number in this region. Let's test a number in this region. And we shade numbers that work. So if I plug in, say, negative 6 or negative 7, is negative 7 less than 2?
Yeah.
All right? So negative 7 needs to be shaded, and so does every other number in this region, because all these numbers are less than 2. What about a number in the middle region, like 0? Is 0 less than 2? Yeah, 0 is less than 2. So all these numbers need to be shaded too. What about negative 4? Is negative 4 less than 2?
Yeah.
Yeah. So it's shaded because it works for that equation. So what about 2? Is 2 less than or equal to 2?
Yeah.
Yeah, it's shaded. All right, what about 3? Is 3 less than or equal to 2? No. But, second chance, is 3 greater than negative 4? Yeah, 3 is greater than negative 4, so it's shaded. And so is all these numbers, because all these numbers are greater than negative 4. And so is 2, and so are some of these numbers. Here is one of the weird exceptions that I was telling you about. Here's an OR graph where it ended up that every single number is shaded because every single number makes one or the other of both, or maybe even both of these statements true. So, in this particular situation, any number is a solution. And I didn't realize that until I got careful in thinking about the graph and realizing that these two inequalities kind of overlapped themselves and made it possible that you could get in no matter what. So, it's rare that you have weird trickery like this, but I decided to show you one just because. I wanted to make sure that you've seen it once with me so that if you see it in a textbook or a quiz or a worksheet or something someday, you know how to handle it. It can happen. The warning I guess I'll give you is that anytime you have one of these graphs, you ought to think about what numbers make it true. Usually there are 3 different regions. Test a number in each region and see if it works. And you can kind of assume that OR graphs are usually the stuff on the outsides. Here it was the stuff on the outsides plus the stuff in the middle because it happened to overlap. So here's a situation where I've got a graph already and I'd like to write an inequality for it. So the top graph there, the numbers between 2 and 5 are shaded, and therefore I need those to be solutions. They need to work. So in order to write an inequality for this particular graph, I've seen graphs shaped like this before where numbers in between things are shaded. That's a great time to use a compound inequality, a sandwich inequality. So I would recommend that you write 2 is less than x, which is less than 5. There's a compound inequality. There's one little issue with this. One of the dots, 2, is shaded and 5 is not. That means that 2 needs to be true. 2 needs to make this inequality work. And so because 2 is shaded, I'm going to add a or equal to clause there. 2 is less than or equal to x would make 2 work. And leave it off with the 5. The bottom graph there is a little more complicated. At its heart, it's kind of an OR situation. I got 2 major regions of numbers, numbers that are smaller than 4 and numbers that are bigger than 11. I also have a few random dots in the middle that are options to be solutions as well. So when you've got lots of different options like that, you separate each of those different options with ORs. And so this first chunk, this is x is less than or equal to 4. This little dot in the middle, this is x equals 6. Just a single number, a single dot is an equals. This little dot is x equals 8. And this chunk over here, those are all the numbers that are bigger than 11. And I'm going to purposefully not put the or equal to clause. Any of these 4 situations, any of these 4 conditions being true gets you shaded. And so when we have a whole bunch of different ways to get in, we separate that with the word or. So I'm not sure I can fit or in here. Or. This big, long statement. X is less than or equal to 4, or X is 6, or X is 8, or X is greater than 11. That's our answer. That's a really nasty compound inequality.
That's a big
So
answer.
I won't give you any of those on your quiz or test, but anyway, that's the extreme example, I guess. So that's and or.